All right, I'm back. We are on page 255, and we are going to keep going. So we want to investigate the limit as x approaches 4 of the absolute value of x minus 4 over x minus 4 equals L. Well, maybe it equals L. We don't actually know. Maybe there is no limit. Let's find out. So first question here is to rewrite this thing as a piecewise function. You maybe aren't as familiar with this type of function as you should be. This is one you want to immediately add into your kind of like mental encyclopedia of functions, right? So you want to know what the absolute value of x over x looks like. So know this, because you're going to get asked a lot of questions about it as you move forward in life. So we want to know that. If we don't know that, it turns out we can investigate it pretty easily. So what I'm going to do is first, I'm going to make like a table. And let's say I put, so this will be x, and this will be like f of x. And then let's call this f of x. All right, so I want to put 4 in the middle. And then I'll do like 4.156. It doesn't really matter. I'll do 3.99, 3, and maybe 0, right? Let's fill it in. So if I plug in 0, I get the absolute value of -4 is 4 divided by -4, so I get -1. If I plug in 3, I get the absolute value of 3 minus 4 is -1. The absolute value of -1 is 1 divided by -1, so that's -1. 3.99, I get -0.01, but divided by, oh no, the absolute value of -0.01, which is 0.01, divided by -0.01, which is -1. At 4, I just get 0 over 0. This does not exist. So you can put any number of things there. I like to put this kind of like the empty set. Some people don't agree with that. You put DNE. You can put undefined. You put whatever you want, really, as long as it's not totally wrong. So everything I said is an option. 4.1 gives me 0.1 over 0.1. So that's 1. 5 gives me 1 over 1. That's 1. 6 gives me 2 over 2. It looks like this function, and it's true, is equal to -1 when x is less than 4, and +1 when x is greater than 4. And it just flat out does not exist when x equals 4. And actually, if we go back to this we can rewrite as -1 when x is less than 0, and 1 when x is greater than 0, and just doesn't exist when x equals 0. An interesting thing about it is that this is also equal to the x over the absolute value of x. Same deal. You get the same exact piecewise function. So like you should know that, because that's an interesting thing, and it'll come up at some points. So if I graphed it, then I would have, let me use a different color to graph this. So -1, +1. So this is 4. Go open circle, open circle. I don't know if you guys still do that in middle school. I think middle school they used to do open circle, where you'd like sit, kind of share your feelings. I don't hear people talk about that anymore, so I feel like maybe they don't do it. All right, we can use our graph now, or we can use our piecewise function to evaluate these limits. Limit as x approaches 4 from the left of the absolute value of x minus 4 over x minus 4 is going to be, from the left, -1. And the limit as x approaches 4 from the right of the absolute value of x minus 4 over x minus 4 is going to be equal to, from the graph, from the table, from the function, whatever, it's going to be equal to 1. And so, therefore, the limit, this is a classic function that does not have a limit, where the limit doesn't exist at a particular value. I shouldn't say it doesn't have a limit. There are lots of limits. There's just one where it doesn't exist, and that becomes the defining feature of the function. It's so unfair. Like every other point, pulling their weight, and then this one point, x equals 4, not doing it. So we just say that this it's not a continuous function. There's a point where, well, actually, that's a trickier issue. Let's not talk about that. Is this continuous? Maybe. Maybe, because we need to talk a lot about that definition of continuity. So there we go. We get that. I'm actually going to look at the next one because it's a calculator problem. So create a graph of this thing. So limit as x approaches 0, sine of x over x. This is a super famous function, mostly because it has a lot going for it. Let's see. So here, I'm going to start a new problem. Doc for 1 graph page. Sine of x over x. Okay, so looking at that, can you tell me what the limit is? I feel like you could. Let me change my window though. So when I change the window, what I like to do, I generally speaking like to use zoom box, but in this case, I'm gonna go like negative 20 to 20 and just go like negative 1.2 to 1.2 maybe. Look at that. So this is an interesting function because as x goes out to infinity, this thing will keep getting closer and closer to 0. So it has a horizontal asymptote. As x goes to negative infinity, this value will get closer and closer to 0. So there's also a horizontal asymptote as you go to negative infinity. It intersects the horizontal asymptote an infinite number of times. This is a classic example of that happening. People are always surprised when a function intersects its horizontal asymptote, even though you see like a lot of examples of functions that do that, especially rational functions where they're like this out at infinity, but in the middle, they're like doing their thing. You can intersect a horizontal asymptote. Definitely. You can keep going back and forth forever as long as you're getting closer to it. But the question here is, what is this limit? So this, you can see, is definitely just going to be 1. But I'm going to trace. So menu 5, enter. Look at that. At 0, it's undefined. Well, what about at 0.01? At 0.01, it's super close to 1. 0.001. It claims to be 1. It is not 1, but it is so close to 1 that the calculator has to round, has no choice. Let's see if we can get it to just say undefined. 3 zeros. I'm just typing them in. 3, 4 zeros. Oh wait, I forgot to put the 1, so obviously. 0.1. Oh, and now it's not doing it anymore. Let's do it again. Menu 5, enter. 0.12345 Ooh, okay, so it's rounding it, but we should check the negative also. Negative 0.00001. 1. We get 1 from the left, 1 from the right. The limit is definitely 1. This is just like an interesting question. So here, I'm in a different problem. So let me add a calculator page. Doc for option 3 for a calculator page. Let's find the limit. So do the limit as x approaches 0 of, I'm going to press the var key so that I can recall the definition, f of x, and press enter, and it just spits out 1. So the limit is definitely 1. It's a removable discontinuity because f of 0 does not exist. So the limit exists, it's finite, but it's not equal to the value of the function. That's a removable discontinuity. This is one that you could remove. So let me go back to the notes and we'll fill some things in. So new share and iPad and go. All right, so we create a graph. So I'm just gonna kind of wing it here, here, and then here. Okay, so let's say this is 1. Do open circle, and then it's kind of like that, and then that. A couple of fun facts about this function. F of negative x is going to be sine of negative x over negative x. But sine is an odd function, so this is the negative sine of x over negative x, which is sine of x over x, which equals f of x. So this is an even function. Sorry, geez, do all the work and then get that wrong. So it's an even function, and that's a good thing to know. Based on the graph, I would say that the limit as x approaches 0 of f of x, so sine of x over x is equal to 1 for sure. You should memorize that limit. It's hard to come up with in any other way. Just memorize it. Sine of x over x. If you think about the graph of sine, it kind of makes sense. So the graph of sine is like this, like this. So this looks, and if you add to that graph, the graph of y equals x, they look really close. And if we were using technology, they'd look even closer. They look like basically the same thing when you're very close to 0, which is why the limit of their ratio is just 1. Like, it makes sense that it would be 1 because they're essentially the same thing. Like, try to guess the sign of 0.1 in radians. It's really close to 0.1. That's like a fun little party trick you can use. The other thing that's interesting, so I'll do this here. This is interesting. We can remove the discontinuity. So if we say sine of x over x when x is not equal to 0, and we say 1 when x equals 0, we removed the discontinuity. We made it continuous. That would be a continuous version. So if I say that this is like g of x, and this is the continuous version of the function, which we've like extended the domain a little bit. We put 0 into the domain, and when we did it, we put it in such a place that it fixed the hole, the removal discontinuity. All right, I'm gonna wrap this up here, and I will be back in the next video to do more. So I will see you then.